Hello and welcome to the CSES problem solving meetup today. If you can hear me fine, please post a message on chat that would let me know that my audio setup is working fine. Thank you, Brooke, for the confirmation on chat. Let us get started with today's problem solving session. Today we've got two interesting problems. These are again introductory problems. We're almost towards the end of the introductory problem set. We have got apple division, which is a small twist on the concept of making all possible choices, which can be encoded as a binary string pattern, and there are other ways to solve it as well. So I'll go through both, and then we have the problem about chessboard and queens, which is also very popularly known as the n queens problem. We have a very small minor twist to it. We will see that as well. Okay, so let us get started. The first problem is apple division. Let's see the problem statement. There are n apples with known weights. Your task is to divide the apples into two groups so that the difference between the weights of the groups is minimal. Okay. The first input line has an integer n, the number of apples. The next line has n integers, p1, p2, and so on up to pn, the weight of each apple. Print one integer, the minimum difference between the weights of the groups. So here's an example. Say 3, this is just the number of inputs, the number of weights that we will receive in our program. And this is the actual input. There are different weights, 3, 2, 7, 4, 1. And the answer for this is 1. So what we're trying to do, we're trying to split these numbers into two separate sets such that the set sum, or I will call it the group sum, the sum of the numbers in each group will take the group sum, and we want that the difference between this group sum is as minimum as possible. So that would be the absolute value of the difference. So in this case, we can arrange this, or we can separate these numbers into two groups in such a way that we can get a difference of 1, and that would be the difference between the group sums, and that is the smallest possible difference possible. In this case, we can pick 2, 3, and 4, put it in one set or one bucket or one group. So it's explained here as well, 2, 3, and 4. That will give us a weight of 9. And then we can group, the second group can have 1 and 7, which will have a sum of 8. And 9 minus 8 is 1. So that is the solution. In this case, we want to print 1. And how do we solve this thing? So here, one of the clues comes from the input size. So this is something that we will discuss in more detail tomorrow in the book reading session. And I want to bring it up. I think I have a board for this as well. I want to make a reference to it. So it'll be a forward reference to something that we will study tomorrow. But sometimes this input size itself can give us a clue, like what kind of time complexity is expected. So let me just see. So one might start thinking if there is some very clever algorithm to do it in, say, a dynamic programming approach or some other clever approach. And turns out there is not. And one clue can come from the problem size itself. So let me open some of the future board fairs that we'll be studying. So the one I want to refer to is estimating efficiency. Yeah, so we'll be looking at this tomorrow. But basically, if your input size is so small, like 20, it's very likely that the solution is O of 2 to the n. It's a very likely possibility. Why we will discuss that? We did allude to it in the previous session, but we'll discuss it in detail tomorrow. And why is so? Why is it so? Because say if there was a better algorithm, then the input test case size cannot be so small. They would have most certainly set a larger test case size to time out the inferior algorithms. So since they have set a small input size, it means the time complexity is definitely pretty bad, like O of 2 to the n, and that's why I've done this thing. So from the input size itself, we can make a fair guess of what the time complexity is. In this case, it is in fact 2 to the n, and what we have to do is we have to make all possible. So we have to basically figure out all possible divisions of this number. So all possible ways of separating these integers into two possible sets, and then do the difference, and then keep track of which one is the minimum, which of those gives us the minimum difference. So there are multiple ways to do this thing. So like for most problems, there are multiple ways to solve it. One easy thing to notice here is that we can use the binary numbers to tell us which apple to pick and put it in which group. So let me see if I've got a board to do an illustration for this. If not, I'll just try to describe it myself. Yes, I have a board. So let's go through this. So say we're given an input 5934. Okay, and I've taken a small input on purpose so that we can illustrate this technique nicely. So say this is a small input 5934. We can just rely on all the binary representations of 4-bit integers. So these are all the binary representations of 4-bit integers, the second column. Of course, they correspond to some decimal representation, so 0 to 15. So we've got 16 possible representations of 4-bit integers, and each representation is telling us where to put each apple. Okay, so if it is 0, let us say we have two groups, left and right. Okay, so I'm just making up terms. Let us say there are two groups, left group and right group. So if it is 0, we will pick the apple and put it in the left group. So that specific apple, which would be the apple corresponding to the weight 4. If this is 0, we do the same thing. Okay, so let us take a more typical example, say this one. Okay, this one is nice, I think. We have 3 apples of weights 4, 3, 9, and 5. This binary string is telling us that we pick the apple of weight 4 and put it in the left bucket. This one is telling us that we pick apple of weight 3, put it in the right bucket. This one is telling us that we pick apple of weight 9 and put it in the right bucket. And this is telling us, this 0 is telling us that we pick this apple of weight 5 and put it in the left bucket. Left bucket. So the left and right I'm representing as minus and plus signs because it just works. The arithmetic just works out. Because what we will do in the end is take the sum of all the apples, sum of all the numbers in the left bucket, and then take the sum of all the numbers in the right bucket, and then do a subtraction. So that is exactly what we're doing. We're putting a negative sign for all the numbers in the left bucket, let us say, and plus sign for all the numbers in the right bucket, and this works out to be our difference. Actually, we are interested in the absolute value, but in this case I've just preserved the negative signs as it is, just to make this illustration clear. But while keeping the minimum, or while doing the bookkeeping for the minimum value, we'll be doing an absolute value and then do the comparison. So I try to explain that in my own words. I've also written it down neatly, so let us see if it can do a better explanation than what I just did. In the table on the left, if a number is prefixed with a plus sign, it belongs to the first group. Okay, just a slight change in terminology. So I'm calling it first group, second group here. I wrote this board quite a few weeks ago, so I don't remember exactly what I wrote. So here it is. So it belongs to the first group. If it is a negative sign, it belongs to the second group. And and then we do a subtraction. The diff column represents the difference, S1 minus S2, where S1 is the number of numbers in the first group. Sorry, is the sum of numbers in the first group, and S2 is the sum of the numbers in the second group. Okay, I think that is straightforward. And a couple of additional notes. There are 2 to the n ways to choose 0 or more elements from a set of n elements. So it's basically, we are seeing a different interpretation of these binary strings. So in algorithms and mathematics and computer science, sometimes we can see the same concept with different interpretations, leading to more insight. So that's what these few notes are about. So each of this binary string is telling us different ways to choose 0 or more elements from a set of n elements. So say the question was, okay, I'll come to that a little bit later maybe. Let's first solve this problem. So I was going to show a relation with making binary choices, but we'll come to that in a while. For a finite set S, where the cardinality of S is n, in other words, where the number of elements in S is n, the cardinality of the power set is 2 to the n. The power set contains all possible subsets. So the number of all possible subsets is 2 to the n, because that is the same thing as asking how many different choices of elements we can make from this n items. So that is one other way to look at it. Yet another way to look at it is this. The binomial n0 plus binomial n1 and so on up to n equals 2 to the n. So each of this term is telling us how many ways we can choose k number of items. Okay, so yeah, I think I'll clarify that now. So I don't want to wait, because there are a couple of points here that are relevant here. So the other side point I wanted to mention was that here we'll be solving the problem of deciding where each apple goes, to the left bucket or the right bucket. We can also see it as a single bucket problem. Like we can say, we can imagine it like we are only making choice for the first bucket. Okay, so this binary representation or whatever technique we use will help us decide which apples to pick for the first bucket. Whatever remains, the remainder becomes the second bucket. So that's one way to look at it. And this kind of problems appear very often in online online judges as well as other places. So for example, another way this problem could be posed is not the specific problem, but a problem that uses this technique could be that we are given a set of say n items and produce all possible subsequences of them, like all possible subsets of those 10 items, which is the same question as the power set. And the again, the number of ways we can choose all possible subsets of items from a given set is 2 to the n. That is what this is talking about. Okay, and what does this one mean? So let us say we have got 10 items. So I'll just take n equals 10 for a very concrete illustration. The right hand side is asking the question or answering the question, how many possible ways we can choose elements from these 10 items. So that would be 2 to the 10, because for every item we take a yes no decision. We either decide to pick it or not pick it, which is the same thing as this binary representation. So either it is 0 or 1, yes or no. We either pick it or don't pick it. So there are n items. For each item we have a binary choice. So we have 2 to the n ways of picking it. What is the left hand side telling? The left hand side is telling, this first term is telling, in fact we'll focus it on term by term. This first term is telling how many possible ways are there to pick 0 items from a set of 10 items, because I've chosen n equals 10 for illustration. So how many possible ways to choose no items from 10 items? That is this first number. This is also often written as Cn0 or nc0 and so on, multiple notations. This is the binomial notation. So Cn comma 0 is another notation. So the answer to this is 1. There's only one way to choose no items, and that is not to choose any item. How many possible ways we can choose one item from a set of n items? So that is nc1. I'll read it like that if you're familiar with that notation. And the answer to that is 1. nc1 is just 1. And so on. How many possible ways there are to choose 2 items? How many possible ways there are to choose 3 items? And so on, up to how many possible ways there are to choose n items. And once we have done this computation on the left hand side, we have actually covered all possible ways of choosing items from a set of n items. So that is why this left hand side equals right hand side. And this is sort of a visual, intuitive proof of this expression. Of course, there's a formal proof. We can prove it formally without much trouble. But yeah, it just makes sense intuitively also that both these expressions have to be exactly the same, because this is all possible ways of choosing any number of items from a set of n items. And here we are splitting the problem into n cases, case 0, case 1, and so on up to case n. Okay, so those were the additional notes. In case if you have any additional ways of interpreting this, please feel free to use the chat or just unmute yourself and talk about it. And now we'll just look at the code now. How do we implement this? So in this case, we are not just interested in choosing items. We want to choose that item, put it into one bucket, consider the remaining items to be in another bucket, then do a sum, then subtract the sums, and then keep track of the minimum sum. So a little bit of bookkeeping, but the essence of the problem is just making this binary choices. So let's see. Here's one possible way of writing code. There are many other clever ways of writing this code. So I've just written something that is simple and neat to look at, hopefully. So n is fine. And then we're reading all the inputs into this vector p, because that was the notation used here. P, let me go back to the problem here. Yeah, p1, p2, and so on up to pn. Okay, so, and this is where we'll keep the minimum diff. This is just, I'm setting it to the maximum possible value for a long, sort of like, it's like it is our acting infinity, I could say that. So it's almost acting like our infinity, just a very large number. And then we will start doing the actual work. And that is, we want to generate all possible numbers from 0 to 2 to the power n minus 1. So that's what we want to do. And that is encoded like this. We are going from m equals 0. So m is for mask. So I'm just chosen the letters as mnemonic. So M is our mask because it will finally give us something that we will treat as a mask to decide whether to pick something for the first bucket or second bucket. So M equals 0, C less than, I think C is for choice probably. So C less than 1, I'm not sure what is the C doing here. This is M. What is this C? Where did I even define C? Okay, maybe this code is in a bad shape. Maybe I made some modification. I didn't test it later, but that's okay. I think this should be M from what I remember. Okay. All right. So we are going to start with M. Go all the way, but not touch 2 to the power n. So this is just one left shifted a number of times. So if you left shift 1 once, we get a power of 2, which is 2. If we left shift 1 n number of times, we get 2 to the power n. So we're going from m equals 0 to 2 to the power n minus 1. And this is the loop plus m. And we'll find the current diff, we'll store it here. The first group sum minus second group sum. And then for each m, for each mask, so this is giving us 0 to 15, in this case say n equals 4. So we're getting all these masks. And inside this loop, we will pick every bit of this. We'll not go through it line by line. This is something I'm pretty sure everybody can figure out, and people may have their own way of writing this thing. So for each of these bits here, we will check if it is 0 or 1, and depending on if it is 0 or 1, we decide whether to do a plus on that number or minus on that number. So that's how I'm keeping track of the two buckets. So one bucket is just plus sign on the numbers, the other bucket is just minus sign on the numbers. So this is the loop, and this is where I'm doing the bit mask operation, basically shifting whatever you've got I number of times, some bit mask operation, and then doing m ampersand, testing that bit if it is 0 or 1, and if it is 1, then I'm considering that to belong to one bucket. If it is 0, I'm considering that to belong to the other bucket. So put some comments here. Yeah, and that way the diff itself will tell us what the final difference is. So I'm not really keeping two separate sums in the same diff variable. I'm managing the difference. And in the end, we do a min diff equals the minimum of the current min diff and the absolute value of the diff. So that's something to be careful about, because we are only interested in the absolute value of the differences. We're not interested in the sign. Yeah, so that's how we keep the minimum difference, and we print it. So that is one approach of solving this thing. Usually if I see a problem like this is the first approach that will come to my mind, because I usually associate problems like this to bit strings in a very natural way. But there are other ways to solve this problem as well, and I'll come to that in a moment. I'll just check if there are any comments anywhere. Okay, no comments anywhere. Let's move ahead and see another approach to this problem. And I see this took a longer time than I had thought, so I don't know how much we'll be able to cover. The next problem in Queens, if you're not able to cover entirely, we'll continue with it tomorrow, and then we have some book reading session as well tomorrow. So the second approach is a recursive approach, and the thing to think about, and this is something I often share while doing algorithms. Say there's a algorithm problem, and we are not able to, we don't have, let us just assume for the sake of argument that we don't have this mathematical insight that these things translate directly to binary strings. So often when we don't have a good mathematical insight, it is often easy to convert the problem to a recursion problem. And it's a trick that comes useful several times. And for any recursion problem, we really need to think two things to get started. Can we make the problem a little bit smaller? Like, can we work on a small portion of the problem and make the problem smaller, so that we can work on the smaller problem recursively? So that's the first thing. And second thing, can we have a nice base condition where we can start returning so that it's not an infinite recursion? So if you have those two things nicely worked out, it's very easy to convert a problem into recursion. In this case, it is. So it's a binary choice problem, right? Every step we are deciding whether to pick this number or not pick this number, or put it in bucket 1, put it in bucket 2. So it's a binary choice at every step. So we'll try to put that binary choice into a recursive algorithm. And let's see, I've got a legend here to help me out. So what's going on here? Let us see that. I put taken the same input 5934 as an example. In the chart on the left, each level of indentation represents recursion depth. Okay, I think that is obvious. I'll be walking through this example in a moment. The first number in each row represents the choice whether to add or subtract, basically bucket 1 or bucket 2. I'm just keeping track of them with the sign plus or minus made for each element. The second parenthesized number represents the current diff computed as a result of all the choices made in the current call and preceding calls. Yeah, I think that makes sense to me because I wrote it some time back, so I'm just trying to remind myself what I wrote. I'll explain it in a while. I hope it makes sense to you. In case not, I'll just explain it in a while. And here's the solution. Okay, I'll go through this text a little bit later. Let us see if I can describe it before. What we'll do, we'll pick this number 5, and there are two possible choices. So we're at the first level of recursion. We have I'll just open the code also on the left side. Yeah, so we have a solve function like this, which is basically a recursive function that will solve this problem. So a solve function will make choices for every number it sees. So we have got 5934. It is seeing the first number 5. It will make two possible choices: plus choice, minus choice. And again, plus and minus are just my notation for whether to put it in the first bucket or second bucket. Okay. And then for the plus choice, it will do a recursion to itself. It will call itself recursively and ask the the next call, the descendant call, to work on the next number. So the recursive call will now work on 9 and make two possible choices, either plus 9 or minus 9. Okay, I'm just going on the upper branch just to show the full recursion depth. And so we have worked on two numbers so far, and if we are in this recursion depth in this first branch, then the answer would be minus 14 because we put both the 5 and 9 on the same bucket, the plus bucket. So the difference is minus 14. Of course, we'll keep the absolute value in the end, but I'm just noting down the difference here. But if we had made this choice, our current running diff would be 4 because 5. What have I done here? Yeah, I think it is minus 9 plus 5. Which would be minus 4. I think I flipped around the signs here. Little mistake there, but I hope the idea is clear. And then let us take this one for example. I think it's a more interesting case. So say we have made the choices plus 5 and minus 9 in the previous two parent calls, and now the recursive call will work on 3. So again, it will take two possible branches, either plus 3 or minus 3, and again it will keep a running sum. So plus 5 minus 9 plus 3. Whatever that sum is, it turns out to be 1, and so on until we reach the full recursion depth. And that thing we have to also be careful about how to detect that we have reached the end. And all these numbers we have to keep track which one of them is the minimum. So one variable we can keep a global variable outside, maybe at the top of the code, to keep track of the minimum. What I usually do, I just keep passing a variable to every function call, reference to a variable. So this is that variable here, mindiff. Okay, I hope I was able to explain that. Let us see the commentary here, what is written here. The solution function calls itself recursively. In each call, it receives the entire sequence of the numbers. Okay, the index of the element in the sequence that we need to work on. So it will get the whole sequence and the index that it needs to work on. So in this second recursion call, it needs to work on this. So index will be 1. So the index of the element it needs to work on, and the diff computed so far, because it needs to receive the diff from the parent call, because it has to just add this or subtract this to that diff that we have received. So that is how we keep track of the running diff. Okay, so we call the indexed element as the current element. There are two possible choices to be made now for the current element. Add the current element to the diff. Yes, subtract the current element from the diff. So two choices really. For each choice, call the solution function recursively with an updated diff and the index incremented by 1, so that the recursive call to the solve function works on the next element. And again, this is something that will work for other types of problems also, where we have binary choices involved. For example, generating, say, power sets of a given set, or printing out all possible ways we can select 0 or more items from a list of items, which is again the same thing as doing power sets. So let's see the code. And as expected, the recursive code here will be much shorter to look at. Here it is. Let us see. Yeah, so this is the same thing. We're just reading the input, and here we're calling the solve function. This is where the bootstrapping is happening. This is where it gets started. We're passing the entire array, and the minimum diff, a reference to minimum diff. So you can see this is a reference. So we're passing the exact same variable to all the child calls, and if they update, this will get updated. That is how references work in C++. And this 0 is the current running diff. No, this cannot be the current running diff. Can it be? Oh, this is the minimum diff, and yeah, this is the current running diff, which is 0 because we have not done anything yet. And this is this last argument is the item to work on. So this is saying work on the 0th item, which is this 5 in this example. In the solve function, the first thing to take care is the base case. So base case is if the item that we want to work on is beyond the last index, then we have the base case. We have reached the full depth. So for example, in this case, the possible indices are 0, 1, 2, 3. But if the recursive call is getting work on index 4, which is one past this array, or which is equal to the length of the array, then we are done. So this is what this is checking. If the item to work on, the index of the item to work on equals the size of the list, then we are done. Just find the min def and return it. That's all. Otherwise, solve it recursively. The first branch is we take a minus decision, like putting it into one bucket. The other one is plus decision for that number, put it into the other bucket. So this is a recursive way to solve the same problem. Okay, so that brings us to the end of the apple division problem. If there are any comments, questions, or other ways to solve it, please use the chat or just let me know by unmuting yourself. Now we will move on to the next problem, which is a classic problem. It's a very well-studied problem. There's so much literature out there for this. And it is called the chessboard and queens problem. So it looks a bit complicated at first glance, like if you're not used to seeing problems like this, but it can be very neatly attacked and arranged into a nice problem that we can then tackle very easily. Let us see. So let's say the problem statement first. Your task is to place 8 queens on a chessboard so that no 2 queens are attacking each other. So in this case, we can call it 8 queens because we're going to be dealing with 8 by 8 chessboard, and the number of queens is also 8. The general version of this problem is called the n queens problem. So we could be given an n by n chessboard with n queens, and then we have to solve the problem. So we have to place 8 queens on a chessboard so that no 2 queens are attacking each other. So that's the problem. As an additional challenge, each square is either free or reserved. So this is the twist. This is not part of the original n queens problem. This is just an additional twist, but this is not a very major thing. So this whole thing amounts to just one small Boolean test in the code. So it's still good to focus on the n queens problem. This thing can be plugged in even retroactively after you have solved the n queens problem. Okay, so I'll just ignore this point for a while. And you can only place queens on the free square. So there is again the twist. So there is a concept of free square and reserved square. So all the dots are free squares. All the stars are reserved squares. So where we cannot put the queen. However, the reserved squares do not prevent queens from attacking each other, which means if I place a queen here, say I place a queen at the beginning of this row, I place a queen at the end of this row, they are still attacking each other. So this star prevents us from placing a queen on it, but they don't prevent the nature of attacking each other. So attacking still works the same way like it works in the regular chessboard. The question is, how many possible ways are there to place the queens so that they are not attacking each other? So that's the question. The input is 8 lines, each of them has 8 characters, each square is either free or reserved, and so on. Now, the naive solution is actually has a very high time complexity if you think about it. So what could be a naive solution? We could pick this cell and test out placing the second knight in all the other possible cells, and then the third knight in all the remaining cells, and that would be huge time complexity, right? Because it would be like 64 times 64 times 64. So in this specific problem, it's almost like of the order of 64 to the power 8 checks that we have to do, if I'm calculating that correctly in my head, which is a very big number. So how can we narrow down this problem? How can we make it simpler? So that's the whole cleverness. So this involves a little bit of cleverness, and we have to figure out that how do we make it simpler so that we don't have to resort to testing out all the 64 cells. And that insight should come very quickly, especially to those who are very used to playing chess. And that is that if we have placed, say, I'll go column by column because that's how I arrange the boards. So let us say I place a knight on this cell. So immediately I know a few things. This whole row is blocked, this whole column is blocked, and even some diagonals are blocked. So for a very simple, it'll take a little bit more insight to code all these things, like this blocking concept. So I'll start with very simple. So there's a very simple solution, and there's a slightly more clever solution. So in the very simple solution, what we'll do, we will place the queen here, and then for the second row, we will place it in all the other places. One thing we don't have to test out is definitely these cells anymore, the first column cells, because that is occupied completely. So after that, we just need to test it, placing here, placing the next queen here, and so on. So each possible way, and so on. So the solution will be progressing in a column by column fashion. We can also arrange it in a row by row fashion, but for the sake of convention, I've chosen going column by column. And what we will do, we will place. So in the first iteration, maybe I can call it iteration. Yes, in the first iteration, we'll try placing the queen on each row one by one of this first column. Now, for each of those choices, we will recursively try placing the second queen on each of the rows in the second column, and keep counting how many ways we are able to place as we keep doing all that. Then in the third iteration, or third recursion, I believe, let me just open the code also. Maybe it'll be easier that way. This is the chessboard and queens 0, 1. Yeah. Yes. And in the second one, okay, and so on. And there will be a recursive backtracking, and that's something to visualize. I don't have any diagrams. I don't think it's easy to make a diagram for such a thing. So let us say we have reached here. So we have placed a queen here, and this is all recursion. So we are trying out all possibilities, and that will become clearer when we see the code. Let us say we figure out always to some way to place it here, and then some way to place it here, some way to place it here, and turns out there is no valid way to place it here on the fourth column, because somehow we have occupied all the possible, like it's blocking all possible things. Let us just assume for the sake of argument. Then, since we are failing at the fourth column, we have to come back to the third column and try a different possibility. Place the queen somewhere else, and then again search. So we're basically doing a search of all the solutions in a recursive fashion, and we have to backtrack whenever we see that we are hitting a no solution. There's no possible way to proceed. Okay, that's a rough high-level overview. I'm not sure how good a job I did to explain the algorithm. I don't have any code written for this. So let's just see the code. I think the code will make it more clear if the description was not clear. Okay, so the first thing is we are reading this whole input, and I'm just storing it as characters here. So I have an input, two-dimensional array, 8 by 8, storing every single character, because this is telling us whether the cell is free or not free. And like I said, if it's not a very important detail right now. If this problem is too complex already, just ignore that detail, the free and reserved concept. We can, for the time being, we can treat this problem as just an n queens problem, where we need to place the queens such that they do not attack each other, ignoring this thing. This thing we can latch on in the end without any trouble. Okay. Now, this is the solve function, which will be solving this problem recursively. It is receiving this entire input, which is not important for the original n queens problem. The board is important. So this is the work board. So this is our scratch pad. This is where we will try placing the queens at different places and see if a solution works out. This is initialized to all false. This is the C++ notation for initializing a complete array to all false. This is a Boolean array. If you're using integers, it will be 0, Boolean, so false. And this is what? Let me see what this is. Column. So we'll be working on the first column number 0. So this is saying work on column number 0. This is the result. This will be the count, all the successful placements. Okay. Now we have entered the solve function. I'll come to the base condition a little bit later, because once we understand how this is working, the base condition will become clearer. So for every column, and I put comments here to make this descriptive, in the current column. So at first we'll receive column number 0. So the solve function will work on column number 0, which is this column. So for the column number 0, for each possible row, so I equals 0 to I less than 8. So I is the row number here, row index. So for each possible row, Forget this for now. This is the free versus reserved concept, so ignore that for now. Check if we can place the queen at the current row and the column that we are solving for. We are solving for column number 0 at this time, and we are trying it for each row. So the first would be row number 0. Row 0, column 0, check if you can place it there. And this is a check function coherent, which will do the check. It will just basically do the inspection of the attacking cells, all the attacking positions, and make sure there is no queen there. We'll see that in a while. So for now, just assume that this is abstracted out in this check function. So that way the problem will become less overwhelming if in case it is too complex to hold it in the head in the beginning. So this check function will do that work and tell us whether this cell is okay for the new queen to go. If it is okay, we occupy that cell for this queen. So this is the first iteration, this is the first queen. We occupy that cell. How? We set that row and column to true. And then we recursively go inside searching for new placements with the second column. So this is call plus 1. That's what we are passing here. And we will start searching for solutions in the second cell. And this result, I'll talk about it in a bit. And once we have done searching the result and we come back to the same level of recursion, so because after we have searched, we have gone fully inside, like a nested, after all these nested calls, it'll at some point come out back to the first row, the call for the first, call for the first column. Then we have to try the second row in the first column. So that is how this loop is going. And then again, it will go start searching inside with all these other columns. And then again, it will come to the first column. And then we need to search for the next row in the first column. So what we need to be careful about is that we free that cell. So we occupied that cell here. We place the queen there in the first row of the first column, or the 0th row, because we have 0-based index, 0th row of the 0th column. We search for solutions, and then we free that cell. And in the next iteration, we place the queen on the first row. Search for solutions, free the first row, continue. Then we place the knight on the second row, index 2. So second row, search for solutions and so on. And that is it. And once we are done, how are we done? So this is being called recursively, right? So this one, when we reach here, this is calling itself to solve the same problem for the second column, assuming that there's a queen occupying one of these places, which was done in the first level of recursion. And we'll continue like that. So at some point we'll reach a call for the third column, then call for the fourth column. Okay, I should really speak 0-based indices, so I'll just try again. So the first call was for the 0th column, then for the first column, and then for the second column, and so on. And this is the 7th column, 0-based indices. And when we get a call for the 8th column, that will become a based condition. So when you've received a call for the 8th column, which is one past, it's an invalid column which doesn't exist here, we know that we have successfully found one placement where we have placed all 8 queens in correct places such that they're not attacking each other. So we received call equals 8. That is our base condition, and we increment this result. And this is again a shared variable. All the calls are referring to the same result because of C++ references. I usually use this syntax. Okay. Now, let me just save that as well. Okay. So this is where we do ++ result and then return. And this solves the problem. So this is the recursive approach. The only little detail that I had omitted, 2 little details that I omitted. So I'll cover that as well. And I'll just take a few extra minutes, maybe 5 extra minutes to cover these remaining details. How do we check if the cell is free or not? So the check becomes quite simpler compared to the naive approach, because we are going column by column. So all we need to do, say we are in this column, we're solving for this column, and we're trying to figure out where to place, we're trying all possible ways to place the queens, all possible ways to place the queens in safe cells, non-attacking cells, or cells which are safe from attacks. All we need to do is check on the left side of the board. That's all we need to do. So left side horizontal, left side diagonal. There are 2 diagonals, one like say this is the cell, one diagonal that is going down here, one diagonal that is going up here. So 2 diagonals. So let us see. So say this is the question being asked to this function. There's a board with some queens placed, and the Boolean values of each of the cell are telling whether a queen is placed there or not. If it is true, the cell is occupied by a queen. If it is false, the cell is not occupied by a queen. It's free. And we are asking the question, is row and column safe? And the assumption is that the problem has been solved for column 0 to column -1. The left side of the board has been solved. We are only working for the certain column. So one thing we'll do is check the current row for an attacking queen. So we're checking the current row. So I've highlighted one cell here just for the purpose of illustration. We'll check the current row on the left side fully to see if it is free or not. So that is this loop. Then check the upper diagonal. Checking the upper diagonal is quite simple. We start with this row and column, whatever row column we are given, and then we do, for every iteration, we do I minus minus, j minus minus. So we just keep decreasing the indices for the row and column. So we keep going up like this and check all the places and make sure there is no at no place there is a queen present. If there's a queen present, we just return false, meaning the check has failed. And then check the lower diagonal. And for the lower diagonal, what do we need to do? We need to increase the row count at every iteration and decrease the column index. So the row index is increasing and the column index is decreasing. That's what is done here. Plus I minus minus j, where I is the row index and j is the column index. And the same logic here. If all of these checks pass, then we are returning true. It means that no queens have been found in these attacking positions. The last detail which I mentioned, which is not too important for this problem, is the concept of reserved and free cell, and that is taken care of here. Like I said, it's just one small Boolean condition. So if we are working on a specific column, say we are working on this column right now, and what we will do in this loop is place this queen at every possible row in this column, every possible cell in this column. So when it is row equals 0, we do the recursion to find out all possible solutions. If row equals 1, we do the recursion to find all possible solutions. When row equals 2, we do not do the recursion because this is a blocked cell. This is a reserved cell. We're not allowed to put a queen here. So we just skip over this and try the next one. That is all this is testing. If the current input row and column is free and it is also safe to put a queen there, then we occupy that cell, do a recursion, and then return from the recursion, free that cell, and then try the next row. So this is the solution. This is the recursive solution, and this is one of the approaches. And Traxxas has a comment there. N queens can also be described in terms of permutations. Count n permutations where I minus j not equals pi minus pj for all I less than j using next permutation. That's an interesting approach. And there's a link also shared. I'll take a look at this after we complete our session. Thank you, Traxxas, for sharing that. So this is a very nice fact to know. And this is why I enjoy having sessions like this, because we often get to learn interesting approaches from each other. So thank you, Traxxas, for sharing that. So this is just one approach covered. There is yet another approach, which is even a more clever and more interesting approach, but that requires more analysis. So we'll continue with that tomorrow. The boards are prepared, so if you want to go through them already, you can do so, but we will be going through them together again tomorrow. And I'll just open that board. Yeah, so this is the board. So in this one, the central idea is to number all the diagonals and all the rows, and whenever we occupy a cell, we already know some things will get a very straightforward manner. That is, this whole row is blocked, this whole diagonal is blocked, and even this diagonal is blocked. So that is represented here, like these diagonals. So we have to do that bookkeeping, to do some bookkeeping to keep track of all the diagonals that are getting blocked and the row that is getting blocked. And when we decide places for the new queen, we can just look up this information from a lookup table, like which diagonals are blocked and which rows are blocked, and just not place our queens there. So it can be done in a much more simpler way, although it's slightly more sophisticated and slightly more clever. That is something we'll see tomorrow. So with that, we come to the end of today's session. I hope you'll return tomorrow as well, because we have an interesting approach to study tomorrow as well. And if then time remains, we'll do a little bit of the book reading session, where we have very interesting discussion about performance numbers, how much code we can execute in a second on these tests, on these online judge systems. So we'll do some discussion around that, which is straight from the book. That is all for today. See you all again tomorrow. Until then, take care and goodbye.